I will now just talk about a few of these big O, and sometimes even I will use the little o result for some important functions, especially as they relate to log and the power, okay, a to the n versus log of n, because we see these kind of functions usually especially in algorithms that are recursive and doing divide and conquer. The log will appear there, and it's very important to understand things about the log function. So one of the things that is very easy to prove, for example, using mathematical induction, is that n is smaller than or equal to 2 to the n for n greater than or equal to 1. Okay, so this basically immediately tells me that n is O, big O of 2 to the n. Okay, now, of course, the result is also true that we also know that n is little o of 2 to the n as well, because n is strictly smaller than a constant, is strictly smaller than 2 to the n in terms of order of growth. Okay, so these, please keep this in mind. They are trivial, right? I mean, like, this is 2 to the n is exponential, n is linear. This should not be a tricky thing for anyone to have in mind. Now, if I know n is smaller than 2 to the n is smaller than 2 to the n, and we know the log function is monotonically increasing, then if I take log of both sides, I will get log n smaller than log 2 to the n. And suppose here I'm talking about base 2. Okay, so this is equals to n. So log n to the base 2 is smaller or equal to n. Okay, so this is another important result, that log n is O of n. Okay, log n grows slower than n. So if we have two algorithms, one takes O of n, one takes O of log n, we prefer the log n. Okay, and in fact, actually, log, if you have a log even on a very large number, log can in a sense destroy a very large number. So for example, let's look at factorial. So if you have the factor in factorial, it is 1 times 2 times 3 all the way to n. Now this is smaller than or equal to n times n times n times n, right? Because 1 is smaller than n, 2 is smaller than or equal to n, 3 is smaller than or equal to n, and so on, which equals n to the n. So from this here, we know that n factorial is O of n to the n. Okay, in other words, we have also n factorial smaller than or equal to c times n to the n. Now, if you take the log of both sides here, so if you take the log of n factorial, and it is smaller than the log of c times n to the n. Now, using log rules, this is log of c plus n log n, right? Because log, please remember, log of a to the b equals b log a. Okay, this is an important rule here. So this is a constant, I can drop it. So log n factorial equals O of n log n. Okay, so when you take n factorial is such a fast growing function. If you take the log of that, it becomes even slower than a quadratic function. It is n log n. Okay, so this is very important to keep in mind as well. Another thing, another result that's important to keep in mind is that if we have a smaller than b, then a to the n is O of b to the n. Okay, so what this is saying is that 2 to the n is big O of 3 to the n, and so on. Okay? And the reason for that is that if I want to use the, and it is also little o as well, little o of b to the n. The reason that if you take the limit of a to the n and b to the n as n goes to infinity, this is the limit of a divided by b to the n as n goes to infinity. And because a is smaller than b, then we have a number smaller than a divided by b is smaller than 1. A divided by b is smaller than 1 to the n, the limit of this function is 0. So a to the n is also little o of b to the n as well. Okay, so keep this in mind. If you look, so 2 to the n is O of 3 to the n, 3 to the n is O of 3.5 to the n, and so on. Okay. Another one I want to mention here is that log n is little o of n, not just O of n, but it is O of n to the epsilon for every epsilon greater than 0 as well. Okay, this is very important here. So log n, for example, is O of the square root of n. Log n is O of the square root of n, and so on. This allows us to do that. And of course, log n is O of n and O of n squared, and so on. The very last one I want to talk about, and it's a very important result, because usually when we do a running time analysis of algorithms, we would say the running time of the algorithm is O of log n. And then the student immediately would ask, log n to the base what? To the base 2, to the base 10, to the base e? And the answer is it does not matter. What does it mean it does not matter? It comes from a very important rule for logs. So if you take log n to the base a, whatever a is greater than 1 here in this case, for example, I can translate that, or can transform that into log to the base b. This is exactly the same as log n to the base b divided by log a to the base b. But log a to the base b is a constant. It's some constant. So what I'm saying here is log n to the base a is really just some constant times log n to the base b. Okay, so you can transfer back and forth between a and b, whether a is 2 and b is 10, it does not matter. So log n to the base a is theta of log n to the base b. Okay, so you can transfer back and forth. This is why when we say the running time of the algorithm, the asymptotically is O of log n or theta of log n. It doesn't matter whether that log is base 2 or base 10 or anything like that. Asymptotically, they are all equivalent. In practice, of course, there would be difference. Log to the base 10 is a smaller number than log to the base 2, but asymptotically, they are the same.